Hello, I wanted to add a little bit of information to the GC video that I linked to the Moodle, just to emphasize a few things that they didn't in their video, which was just intended as a general introduction and makes a good overview of a lot of factors for gas chromatography. But because you'll be using our specific GC, I wanted to include a little bit of information about it and emphasize some data analysis details here. So, first I think I'm going to talk a little bit about detectors because they kind of wave over that really fast. And they used a lot of abbreviations and then they didn't really define any of them. So, they mentioned thermal conductivity, but they just put the TC there. So let's talk about thermal conductivity detectors for a minute. Conductivity. Okay, so as they mentioned, thermal conductivity detectors can detect anything. And so this is one of the advantages of having a thermal conductivity detector, but they are a little less sensitive than some, and so that might be a reason why you don't include, you don't select for a thermal conductivity detector. So the way that the thermal conductivity detector works is you need to kind of know what thermal conductivity is. And it's not something that we tend to talk about in chemistry classes much. Usually we just talk about electrical conductivity. So thermal conductivity has to do with how heat flows through a material. And it actually goes very closely with electrical conductivity as well. So what we're looking at in the detector area, there is, of course, the carrier gas is flowing through this. And so if you have your detector right here, then you can measure your thermal conductivity across this area of your detector. And as the gas goes through, the thermal conductivity would stay constant if the gas is just one item. So for example, if you're using helium gas for your carrier gas, or argon or nitrogen, whatever you have, then as long as that gas stays consistent, the thermal conductivity is going to stay consistent also. But as soon as you have your analyte coming through, and the analyte is the thing we're analyzing for, as soon as we have something else in this thermal conductivity conductor, that's going to probably decrease the thermal conductivity, and it just happens that helium gas has a very high thermal conductivity. So the analyte probably decreases the thermal conductivity, and that change in the thermal conductivity is what's detected. And so then the instrument translates whatever that signal is into some kind of peak, and away you go. The other detail is, of course, that if you go with a lower flow rate of gas, okay, I can't talk and write today. Flow rate. This is more sensitive. So if you do only have access to a thermal conductivity detector and you're worried about being at the detection limit, then you can slow your gas flow down and try and hope for the best. Right. So that's one of our two types of detectors that are the most common. The other one is the flame ionization detector, and that was abbreviated FID. And this is what we have on our gas chromatograph. All right. And so for the flame ionization, because you are using some kind of flame in here, that means you need to burn your sample, which means that this is a destructive technique. So you can't use your sample for something else afterward, which can be a disadvantage. You wouldn't want to use this with some sample where you only had a little tiny bit and it was some precious thing. But for many applications, this works just fine. So anyway, the carrier gas has to be able to burn. So that means that what we do is we use a combination of hydrogen gas and air. And so hydrogen gas is flammable, air has oxygen in it, and so together these guys are going to be able to burn, and away we go. So when we do this flame ionization, we also have to have analytes that can burn. So these are usually organic molecules. Right. And then the way that this detector works is that you've got your flame in here, and so your carrier gas is coming through, and it's burning as it goes through, and then, you know, some of it's obviously not, and going to the exhaust. And so here's your detector right over here, and so as you have an analyte coming through, it's going to enter the flame, and it's going to burn, and as you look at the name, it's called flame ionization. So some small amount of the atoms or molecule fragments as it burns, they turn into ions. And so if you've got a bunch of ions that are forming, this is now going to change the voltage across the detector. So you can set this up with a lot of different stuff. So you can have your magnets, you could have your ions that are then traveling across and encountering your magnet, changing a voltage, or excuse me, changing a current. The current gets converted into a voltage, and this is what you are detecting. So the voltage changes when we have an analyte coming through is what's being detected, and then of course the amount of change in the voltage is going to be translated into some kind of a peak height, and that's the same thing that happens up here too, so that your sample is going to be detected for some period of time. And that is also, if we look at the scan of what we are looking at, regardless, we are going to have time, and usually this is minutes or hours, and then depending on what your vertical axis is, you know, if you're measuring voltage, it might be in millivolts or something like that. And as I kind of mentioned, what you are going to see is that this graph for the sample, it draws itself in real time. So as you start taking data, time 0 is here, and you will see a baseline starting. And when the solvent comes through, you'll see that really big solvent peak. It usually gets maxed out in some way. And then you keep on going, and then you get to maybe your first analyte, and that has a peak, and maybe it's nice and smooth, and maybe it has little shoulders, you never know. And then you keep on going, and maybe you've got another analyte, and they don't necessarily have the same height. But that's kind of what your scan is going to look like, and eventually things stop coming off the column, and we call this eluting. As they come out, they are eluted out of the column. And then the amount of time that it takes, this is called the retention time. So gas chromatography is actually really similar to, if you remember from liquid chromatography. So with liquid chromatography, you have some kind of a solid substrate, and you're going to set up your sample, and you're going to put it in some kind of a container with some liquid in here, and you're going to have your samples set up. And the capillary action is going to draw your liquid, which is your mobile phase, up your stationary phase. And as the samples go, you're going to end up with separation. So if these guys have different things in them, then depending on what is inside that sample, then maybe you get, maybe there was a mixture in here, and so you're going to get these little peaks that show up at different places on your sample depending on what's in them. And then when you stop, you mark the end, and then you mark how far each of these samples went, and that tells you, how you identify your peak. So this is very similar to what's happening in gas chromatography. You have inside your capillary tube, you've got your stationary phase, that is the tube with whatever coating it has on it. And then you've got the gas, and that's your mobile phase. You're doing separation by basically this exact same process that we did using liquid chromatography. It's just a lot fancier. So all of the things that you learned about liquid chromatography basically still apply to gas chromatography. All right, so that's sort of a little bit of a basic on the detectors, and now I want to spend a couple more minutes talking about how to analyze your samples. So when you look at this kind of curve here, where we've got our samples coming out at various different retention times. One of the things about the peaks here is that different analytes are going to respond in the detector in different ways. So just because I have, let's say I had 500 micrograms of sample 1 for whatever this peak is, and maybe I also had 500 micrograms of sample for this other analyte, but they don't have the same peak height. And that is just because the different detectors respond differently to different analytes. They don't all have the same response in the detector based on the peak area. So that means that we have to do some calibration to be able to figure out what we're doing with this sample and which of our analytes we're looking at. So there's a couple of different steps to that. One of them is that we're going to look at retention time. So retention time is diagnostic as long as we're keeping all the details of our scan the same. So as you might imagine, there are some different things that can affect what the retention time is. So let's look at that for just a second. So obviously, the identity of the molecule is going to affect its retention time, because that's going to depend on how long it stays in the column. So just like with our liquid chromatography, if we were doing chromatography and we have some polar analytes and we use a non-polar solvent, those are going to come up the column really slowly compared to if we use a polar solvent. So that's also still going to be true about the retention time in gas chromatography. So it's going to depend on the size of the molecule and the boiling point, and in other words, what kind of volatility it has, and then what the molecule's characteristics are like. So I'm just going to put intermolecular forces of the molecule, because that's going to determine how much it sticks to the stationary phase inside that column and how fast it goes through the column instead. Right? So, and all of these are really tied together, of course. The boiling point is tied to the size and the volatility. The intermolecular forces are affected they affect the boiling point. So this is all kind of, one big thing. So clearly the identity of the molecule is going to affect the retention time, but we also have the flow rate of the gas. So we can choose how fast we run that gas through there, and of course the faster the gas goes, the more the molecules are going to get pushed through there, and so that's going to decrease the retention time. And then, of course, the nature of the column, and I'm going to specifically say the stationary phase, so what kind of a stationary phase coating it is, and then the length of the column, because the longer the phase, of course, the longer the column, the longer it's going to take for the molecules to elute out, even if they are coming out really fast. And then finally, the other factor is the temperature profiling. So as you saw in the video, the GC is basically an oven, and you can change the temperature in the oven. And so often what you do is that if you look at the temperature over time, is you start the temperature at something modest, like, I don't know, 125 or 150 degrees Celsius. And then you hold it there for a while just to kind of get everything oriented and load it onto the column. And then you start to increase the temperature slowly over time, and then maybe you increase it a little bit faster, and then maybe you hold it at a higher temperature for a while, and then you start cooling it down again until you get down and you're all done with your run. So the specific details for how you choose to program the temperature of your scan are going to affect how fast things come off, because of course, even for something larger, as you increase the temperature, that's going to increase the energy of the particles so they can move around faster, and that will move them through the column a little faster. So those are all different factors that affect the retention time. And that's specifically the retention time. But if we're looking at peak area is kind of one of these difficult things because every instrument is a little bit different from each other. So this is more qualitative. But we can be quantitative when looking at the peak areas if we are a little bit careful, because what we want to do is we want to figure out how well the detector responds to a specific analyte. So how to be quantitative. So you could, of course, create a calibration curve where you put together a bunch of different samples with different concentrations of an analyte in them, and then you run them all through and you look at the peak area and you create a calibration curve and do some Beer's law kind of stuff. But the only problem with this is that you have to make a lot of samples. Often these runs take a decent amount of time, 20 or 30 minutes, sometimes more. And so this is a pretty time-consuming thing to do. So the other way that we do this is we usually do an internal standard, and then we figure out a response factor. And so what we're doing then is we are saying, well, every single sample that I put in, I'm going to put something specific in it that will be detected that doesn't overlap with my retention time for my peak location, so I don't have to worry about peak mixing here. But I can look at how big that peak is, and I can compare my other analyte to it and figure out a response factor relative to that, and I can use that to figure out an unknown. So the way that we do this is with this little equation, and I'll define the terms here in a second. Okay, so F is that response factor, and then X here, this is the analyte. And so concentration can be any kind of unit as long as your units are the same. And this is the area of the peak, of the analyte peak. And S stands for sample. So this is, this is your standard, not sample. So this is the area of the standard that you are including, okay? So if you create a scan and you, of course, need to know which peak is which, so you run your first scan and you run it with just your analyte, and so you know where its retention time is, and then you do another one with just your internal standard and you know where that one is. Okay, so maybe you have something that looks like this. And maybe this is our standard, and maybe this is our analyte. Okay, so when we do the measurement, maybe this area is like 180 units, and they're just area units. You don't need to worry about what the units are because they're all going to cancel each other out. And so maybe when we did this original scan, we put 10 micrograms per milliliter in our sample for both of these. And so you can see that even though we had the same concentration, the two peaks are not the same area, and that's very, very normal. So if we did the math here and we put these guys in, the X, their area is 180, and then we've got 10 micrograms per milliliter. And then F is what we're solving for. So over here we've got 450 over 10 micrograms per milliliter. And so if we solve for that response factor, you can do the math, you get 0.4. So in other words, the analyte is detected better, or excuse me, is not detected as well as the internal standard is in this particular example that I made up. Okay, it doesn't necessarily have to be the same. So now you run another sample with an unknown. So let's say that you do this other sample now. And so here's your solvent peak, and here's your internal standard peak, and now here's our, I didn't draw that very well, I didn't mean to make them almost the same size. But anyway, we'll make this one a little bit bigger. So now our standard still has 10 micrograms per milliliter on it. And let's say that this time we only got 425 units of area. They are not always exactly the same, and that's okay because we're comparing them, and that's what our response factor is. It's just talking about a relative response. So this time this is our unknown, what the concentration is, but the area, let's say, was 225 units. So now when we run this through, we're going to say, okay, we got 225, and then we're trying to find the concentration of our analyte. Our response factor is 0.4, and we got 425 over our 10 micrograms per milliliter. And so if we solve for this, you can go ahead and do that and double check me. We get like 13. And so now we could use this process to find what the concentration is of an unknown inside that sample. So this is the kind of analysis that we're going to be doing with the limonene and the orange oil. Is we're going to be trying to extract the limonene, then we're going to use an internal standard, and we're going to try and figure out what concentration we have by doing a spiked sample with some knowns in it and calculating our response factor and then analyzing the unknown. So hopefully this answers your questions about doing any quantitative analysis with gas chromatography, and this is intended as an introduction. So there's certainly lots of topics that we didn't cover here, but I think this is enough to get you started. So let me know if you have any questions.